Sarah.
Thank you. Can you confirm you can see the slides okay, Peter?
Yes, absolutely, we can see them.
Brilliant, thank you. So good evening, everyone. Welcome to the final evening. So as Peter said, for this last talk, we return to the theme of quantum technology. And so you've seen various aspects of quantum technologies throughout the school. Hopefully many of you had a chance to watch the introductory video by Paul Griffin, where he gave you a little bit of an overview of quantum technology. And on Monday's talk, Adam Tomiza told us a bit about how we can use quantum physics for more secure communications. Tonight, I'm mostly going to be focusing on quantum computation. And this is a field that's really seen a lot of development very quickly in just the last few years. So it's been around in some form or other for a while, but it's really seen a lot of experimental and industrial development very recently. How I'd like to do this talk is I'll try and give you a little bit of background and a bit of context, and then I'd like to introduce just some puzzles for you to have a think about. And then we'll take a 10-minute break where you can have a think about them, and I'll give you somewhere where you can submit your thoughts. And then when we come back, I'll try to explain what these puzzles I've set have got to do with quantum computation. So hopefully it'll be fun for us all. Okay, so just to set the scene, we ran this quantum technology school first. Oops, I've gone too far forward, skipping ahead. We ran this school first about 4 years ago. And as I say, quantum computation has really advanced really quickly in a short time. So some of these things that I'm about to tell you, I couldn't have said 4 years ago. And so let me just tell you a little bit about what's been happening. So 2018 would have been the first time I could have said that there existed quantum processors. So there have been a lot of both public and private investment, so from firms and also from government. And in 2018, there was various companies that had small quantum processors. So these are just some of them. There's actually quite a lot of companies now, but these are kind of the biggest players. So Google, Intel, and IBM, and you'll see they all have about 50 to 70 qubits. So qubit, I won't go into in too much detail, is just the quantum equivalent of a bit. But this will give you an idea of how small these devices are. If you think about your phone, what memory you've got in your phone, it's probably measured in gigabytes. And so these are really small devices. They're the equivalent of just a handful of bits, so 50 to 70 bits. They're also quite noisy. So what this means is we don't yet have quite good enough control for these to be perfect devices, for them to be able to do the really useful things that we think quantum computers will be able to do. So they're small and noisy devices, but there's a lot, as I say, there's a lot of development happening. So I gave you a preview earlier. In 2019, skip ahead just 1 year, Google were the first to claim quantum advantage. So by this, I mean they were the first to claim that they were able to do a computation or a calculation on their quantum chip that would not be possible on a classical one. So this is pretty exciting. So they claimed that they could perform a calculation using their Sycamore chip. So this one of about 70 qubits, this little thing here, in 200 seconds, that they said would take the world's most powerful computer 10,000 years to solve. So that's quite impressive. I should say that a few days later, IBM, who are also in the race, the quantum race, and also happened to have built the world's most powerful computer, came back and said, actually, we think our computer could solve this in about 2.5 days using a slightly different method. I think, though, that should not detract from the magnitude of this achievement. So if you think about it, I stressed how small this device is. It's got about 70 qubits in it. And this is the world's most powerful supercomputer. So got terabytes of
I'll take it, Dad.
And so it's really a huge achievement to say that this tiny quantum chip could solve some problem in 200 seconds that the world's this most powerful supercomputer would take 2.5 days. I say it's a tiny chip. This is all the apparatus that goes with it. So it's a small chip, but it needs to be cooled. It needs control wires. It's not at all yet anywhere near the level where you'd have it on your desktop. So this is what it looks like in the lab, Google's chip. Fast forward one more year. So this was announced just about 2 weeks after the Quantum Technology School last year. So towards the end of 2020, one of the world's leading groups in China announced that they had used a photonic quantum computer. So that is one that uses particles of light or photons, again, to perform a calculation in 200 seconds that they estimate would take a staggering 2.5 billion years on China's Taihu Light supercomputer. So again, pretty impressive. So the circuit they used at the time was not programmable. So it was a particular circuit set up to do this calculation, which they knew would be hard on a supercomputer. There's been some development since, but I think this is enough to kind of give you an idea of where the field is at. So they do have a programmable version now, which is more versatile. So what I'm going to try and get across in the rest of the talk is what we have done, or where we are at in the field with quantum computing, and what we haven't done yet. So to be perfectly upfront, I say they've done these calculations in 200 seconds that are just not possible on a classical computer. However, they haven't done anything useful yet. So these are specifically designed calculations which are hard to do classically. They're not particularly useful calculations. So I'll try and give you a flavor a little bit later on of what this calculation is that they've done. So it's not hitting the stock market yet. Well, actually, that's not quite true. That there are companies on the stock market, but we're not quite at the point where we've got really useful quantum computing devices, but we're getting there, and it's moving really quickly, and it's quite an exciting time to be part of the field. Okay, so shortly I'll give you, as I say, 3 puzzles to have a think about, and then we'll come back and I'll try and explain what they've got to do with quantum computing. But before I get to the puzzles, let me briefly talk about some physics. So what is the physics behind all of this? So let's start with interference and photons. So if you did physics at National 5, you probably have seen experiments like this that show that light is a wave. If you're coming to us from the computing science side and haven't seen it, don't worry. We talked about it briefly earlier in the week. But these are the sorts of experiments that show us that, that light has a wave behavior. So if you shine a source of light at a slide with 2 slits in it, then you get this very distinctive pattern on a screen. So you collect the light on a faraway screen, and you get a very distinctive pattern which has bands of light and dark. And this is a signature of wave behavior. So this is an example here at the bottom of the actual interference pattern that you would see if you could. This is just a photograph of such an experiment. So why is this a signature of wave behavior? If you think of how a wave works, as a wave approaches an obstacle, these 2 slits here act as a source of waves. And so from each of these, there's waves emanating. And where the waves from each source meet, in the middle, you can see that they produce this quite distinctive interference pattern. So what's happening is that the waves from each source are adding where they meet and producing this pattern. And this is exactly analogous to what you would see on the surface of water if you drop 2 stones on the surface of a pond and saw ripples coming out of them. Where those ripples meet, you would see this sort of pattern. Okay, so how does that relate to this sort of distinctive pattern that I said you see in this double slit experiment? Here's a schematic of that sort of experiment. Here we've got the double slits and a screen at some distance to those. And when the waves come out of each of these slits and make their way to the screen, if we're looking at a point on the screen where the waves are meeting out of phase, so that is the peak of one is meeting with the trough of the other, then you get destructive interference. That is, they completely cancel each other out and it looks dark. So it looks like there's no light there at all. On the other hand, if you look at another position on the screen where they're meeting in phase, so the peaks of one wave are meeting with the peaks of the others and the troughs are meeting with the troughs of the others, then they're adding to make a bigger wave and a brighter spot. And you see a bright spot here. So if it's in phase, you get constructive interference. If it's out of phase, you get destructive interference. And this is what gives these very distinctive bands of dark and light. So these sorts of experiments show us that light is a wave. We also, however, know that light is made up of particles. So it was Einstein, in fact, that was the first to suggest that light was made up of particles, which we now call photons. And this is what Einstein actually got his Nobel Prize for. And so we know that each of these photons still has this wave-like behavior. And we know that because we can do exactly these interference experiments, but do them with single photons. And so if you do the same kind of experiment, but you send through one photon at a time, then this is what you see. So let me just wait. Let me get back to the start. At the start, where you've got just one photon coming through at a time and you're not seeing very much yet, where they're hitting the screen looks more or less random. So it looks sort of random. But as more and more particles come through, you see this very distinctive interference pattern build up. Now, because we're doing this experiment one photon at a time, this really is exhibiting that every photon individually is demonstrating this wave-like behavior. So we know that light is made up of photons, but we also know that each of those photons behaves like a wave. Okay, I'd like to introduce a couple of other ways of seeing this phenomenon of interference, because it's really fundamental to what's different about quantum versus classical and the working of quantum computers and other forms of quantum technology. So first, let me introduce a 50-50 beam splitter. So we mentioned this, I think, in Monday's talk about when Adam Tomisa showed us the experimental setup. A 50-50 beam splitter is essentially a partially silvered mirror. So it partially reflects the light that hits it. So if you have light coming in from this side, then half of it gets split. So half of it is transmitted and half of it is reflected, but coherently. So you could recombine these and see interference later. I'll come to that. But if you put a detector in each arm, then half the time you would see the photon, you would see the light here, and half the time you'd see it here. Now, similarly, if the light's coming in from the other side, you get the same effect. So with probability of half, it's reflected, and with probability of half, it's transmitted. And this is just a very simple component that forms the basis of many interference type devices. So this is a lovely example. Interference is one way of measuring distances very accurately. And one place where this is used is by LIGO, who detect gravitational waves. And they do a lovely animation showing how this interference works. 1 minute. There we go. So you should see the light coming out, meeting the 50-50 beam splitter. Some of it goes one way, some of it goes the other way. It hits the mirrors, comes back and recombines at the beam splitter, and then we can have a look at the two output ports. Now this part shows the explicit, there's a wave in there. So what happens to the waves as this happens? Again, the light splits, goes down the two arms, comes back, recombines here. In this arm, you can see the waves are canceling each other out. So they're out of phase, where one is a peak, the other is a trough, and so it adds to 0. In the other arm, it's constructive interference. They add coherently, and they give you a stronger beam. Now, what they're showing here is as those mirrors move, as the length of the arms changes slightly, then this changes what happens here when they're recombined. Let me just replay. So there's the light going, recombining, and as the mirrors move, then the length of each arm is changing, and what's happening when the beams are recombined is whether they're in phase or out of phase is slightly changing. So here we see again them hitting the mirrors and coming back. And as these mirrors move a little bit, it changes this condition of perfect destructive interference here. And so some light leaks into this port where previously there wasn't any. And so just by seeing some of that light leaking in there, we know that the length of these arms has changed. And this turns out to be a really sensitive measurement of length, and this is why it's used for gravitational wave detection. So as a gravitational wave hits the Earth, it changes the length of the arms relative to one another. And this is how we measure them. Well, not me, but how we measure gravitational waves. Okay, so generically, interferometry is a really useful technique to measure things accurately. And so just one more simple example of that. So this is possibly one of the simplest configurations of an interferometer. And the idea is very similar to the animation that we've just seen. But I'll discuss this apparatus a little bit later. So just like, sorry, there we go. It's exactly the same idea as the previous animation. At the first beam splitter, the light can go one of two ways. And at the second, the two paths get recombined. And then we have a detector here in each output to see what happens. So as before, if these two arms are exactly the same length, then all of the light comes out of one port. This is a very simple animation. It's not as as good as the LIGO one, but here is a schematic of a pulse of light, which you can imagine contains just one photon entering the apparatus. So as it enters, when it hits the first beam splitter, it gets split and goes down both paths. So I've changed the color here slightly to demonstrate that it's not just in, the photon is not just in one path or the other, but is actually split across both paths. It then makes its way through the apparatus, hits the second beam splitter, where the two paths recombine. And if these arm lengths are exactly the same, then we get constructive interference up here and destructive interference here. And it all gets recombined and goes into this one output port. And we see a click in the detector here. On the other hand, if the arms are different lengths, then just like in the animation earlier, you can get light leaking into the other port. In particular, if one arm is longer than the other by exactly half a wavelength, then when they arrive here at the second beam splitter, they arrive just out of phase. So if it's half a wavelength difference, then the peaks of one wave will combine with the troughs of the other. And now we get completely destructive interference up here and constructive over here. So in this case, again, our pulse gets split at the first beam splitter, makes its way around. And now when they recombine here, one is shifted relative to the other, and it all goes into the other arm. And so by any slight change in the length of the paths, you get a change from seeing all the light here to some light in both arms to all the light here. Okay, and we'll come back to this a little bit later. Okay, so the other little bit of physics I wanted to mention again is polarization. And hopefully many of you had a chance to play with the polarizers that we sent around in the activity packs. So this is sort of revision and a little bit of why polarization is useful and where else it's used. So polarization is one aspect of the wave nature of light. The direction of oscillation of the electric field, so in particular light is an electromagnetic field, so that means it's made up of electric and magnetic fields. And the direction of oscillation of the electric field is the polarization. So as I say, hopefully you got to play with some of these polarizing filters last week or this week. And here are some examples. So if the electric field is oscillating this way, then you get horizontally polarized light, this way vertically. And you can also have all of those in between, so diagonal and anti-diagonal and so on. So polarization is one example of a quantum property, and this is why it's useful in communications, as we saw on Monday. But it also has lots of other uses, and it's worth just sort of mentioning that it's used in many other ways. So one place where polarization is used is in 3D cinema. So probably you've never thought about exactly how this works. But when you are just looking around you, the view that one eye gets is slightly different from the view that the other eye gets, just because they're not in exactly the same place. And it's in your brain, of course, that you combine these two images to give you a 3D picture of what you see around you. Now, in 3D cinema, if you can direct one image to one eye and a different image, slightly different image to the other eye, then you can trick the brain into thinking that it's seeing 3D and reconstructing these three-dimensional pictures in exactly the same way. And so this is one way in which polarization is used. If you have a polarization filter one way in one eye and the other way in the other eye, and project these pictures using polarized light, then you can direct one image to one eye and one image to the other. So that's one use. So the only new thing I wanted to introduce about polarization, you've seen polarizing filters, is one other type of material that we can use to control polarization. So this is a new thing that I'd like to introduce, something called a half-wave plate. So a half-wave plate is made up of a somewhat exotic material, which has a different speed of light for different polarizations. So there's a special axis called the optical axis, marked here. And light, which is polarized along this direction, along the optical axis, moves a bit faster than light, which is polarized orthogonal to it. And so this is the effect. So suppose we've got an input light, which is polarized at 45 degrees. Then this is made up of some horizontal light and also some vertical light. So when it enters the material here, the horizontal and the vertical components are in phase. So what I mean by that is here, the vertical is at a maximum, it's at its maximum up, and the horizontal is also at a maximum, it's maximum to the right. And when you combine these, this gives a net effect that it's a diagonally polarized vector. Now, if you can see well enough, as these progress through the material, the blue ones, the horizontal one, is moving slightly slower than the green one. And so it's just getting slightly out of phase. Each cycle, it's getting slightly further behind. And if the thickness of this is chosen correctly, then by the time you get to the outside, it's out of phase by half a wavelength. And so now at the other side, where we've got a maximum vertical pointing upwards of the vertical component, the horizontal component is no longer pointing to the right, but now it's pointing to the left. Okay, and so when this recombines, we get not the diagonal polarization anymore, but the anti-diagonal, the orthogonal one. And so this is one way in which, just another way in which we can control polarization. So we looked at filters, which blocks one polarization and lets the other one through. This actually changes the plane of polarization. So this is just an animation showing the same sort of thing. Here it's tilted compared to the last diagram. The optic axis here is at 45 degrees and the input light is vertical. Otherwise, it's the same idea. So it's showing the full polarization vector. So you can see that as it moves through the material, the polarization is vertical. And because one component is slightly slower than the other, then it's just slightly changing as it's moving through. And by the time it comes out here, it's horizontally polarized. So the polarization is changing throughout, and until at the exit, it's now horizontally polarized. So this apparatus is called a half-wave plate, and something you would actually use in the lab looks like this. And if you used, so you looked last week at cross polarizers. If you have one polarizing filter and then put another one at right angles to it, then no light comes through at all. If you were to put one of these devices in between those two, then it would, because it rotates the plane of polarization in between, you would be able to see light pass through again. So just a summary of what that actually does. So what's the effect of a half-wave plate? It slows down one direction of polarization relative to the other one, and it has this effect of therefore changing the polarization. And so for some examples, if you put in horizontally polarized light, it gets rotated to vertical. If you put in vertical, it gets rotated to horizontal. if you put in light which is aligned with the optic axis, so it's diagonal, then nothing happens, it just comes out as is. If you put light in the orthogonal direction, then this gets slowed down and it's out of phase by half a wavelength by the end. And so that means that the peaks are turned into troughs and the troughs are turned into peaks. So it's like multiplying by a minus sign. So that's why I've got this minus sign here. Okay, so that's enough now to introduce the puzzles. And then I'll give you sort of 10 minutes to go away and think about them. And it's really just to give you a chance to kind of engage with them, and then we'll talk about them together afterwards. So we don't need lots of quantum mechanics to talk about these, but when we come back, as I say, I'll try to explain what they do have to do with quantum computing. So the first one is to do with this new piece of apparatus that I've just introduced. But when I direct you to where to give your answers, I'll give you that information about the half-wave plate again, so you can have a look at that again. So this is the first puzzle. You're shown to your lab and you're given two pieces of equipment. They both look like this. So they look like they're half-wave plates, but you can't be sure. You are told that each one is either just made of glass. So if it's just made of glass, it doesn't do anything to polarization, or it's a half-wave plate. So it does change, it can change the polarization. Otherwise, they're the same width, they look the same otherwise. You're asked not what they are, not to determine whether each one is a glass slide or a half-wave plate, but just whether they're the same or not. Okay. So just whether the two pieces of apparatus are the same or different. And the puzzle that I'm setting for you is to think about what is the minimum number of photons you need to determine whether these are the same or different. Okay, second one. So we introduced earlier a 50-50 beam splitter. And this is, as I say, a partially silvered mirror. So if you put in light at one side, then it splits, half of it comes out one side and half of it comes out the other side. What I'd like you to think about is what happens if you put in two photons at the same time. So you've got this beam splitter, you put in one photon in each input port. And the question for you is, with what probability do the photons exit in different ports? And again, I'll explain what this has got to do with quantum computing when we come back. Okay, last one. So for this one, the puzzle itself has got nothing to do with quantum yet. I'll tell you later what the relationship to quantum mechanics is. This is a sort of prisoner's dilemma. So it's if you've heard of the prisoner's dilemma problem, it's not exactly the same. It's sort of a variation on it. And here's how it goes. Imagine that there are two prisoners held by a cruel captor who gives them one opportunity to win their freedom by playing a game of chance. The rules are laid out in advance. So the captor tells them what the rules are. And they're even allowed to talk about what their strategy would be briefly before them being sent away and locked in separate cells. And they are unable to communicate further. Okay, now here is the game. Once they're separated in separate cells, the captor comes in separately to each one and asks each prisoner just one question, chosen at random from two possible questions. So the question isn't set in advance. He could ask one of two possibilities. So he could ask prisoner A question 1 and prisoner B question 1, or he could ask prisoner A question 2 and prisoner B question 2, and so on. So he'll ask just one of these combinations. The rules are that each question has a yes/no answer. So each prisoner has to answer yes or no once asked a question. And the answers given must either agree or disagree as specified below. So what does this mean? If the capture comes in and asks prisoner A question 1, and then goes into prisoner B and asks question 1 also, then the answers they give, they can be either yes or no, but they must be opposites, they must disagree. So if prisoner A says yes, then prisoner B must have said no. And similarly for other combinations. If they chose to ask question 2 to both prisoners, then again, their answers have to disagree. So the question for you is there a strategy that the 2 prisoners can agree on that allows them to win and win their freedom? And if not, then with what probability can they win? Finally, there's a slight variation on this, in which the rules are just slightly changed. So all the other rules are the same, except that the pattern of whether they need to agree or disagree is just slightly changed. So now if both are asked question 1, then they must give the same answer, either both yes or both no. The others are the same. If this is the game, then now is their strategy which allows them to win. And if not, with what probability can they win? Okay, so it's a few things there. If you follow this QR code, you will find a form which restates the questions and also should give you the other information from the slides that you need. So about the half-wave plate again, what a 50-50 beam splitter is, and so on. I will also put in the chat the link to that if it's easier. Boom. And we will pause for 10 minutes for you to have a think about each of them and send in your results. And as I say, it's just a chance to give you a chance to think about them. Don't worry about whether you get them right or not, just sort of have a think about each of those puzzles. And when we come back, I'll tell you a bit about how they are related to quantum computing. We'll take a 10-minute break and come back just before quarter to 8. Let's all come back and talk through the different puzzles. Really nice to see all the results coming in. So well done, everyone, and thanks very much for engaging. I've posted into the chat the link to, should be the link to the responses. It's a bit tricky for me to share both the slides and the distribution of the responses. So I've put the link in so you can have a look yourself if you want to. So we've got 27 responses, which is great. Out of this, 34 was on the call, and some of us are organizers. So 28, brilliant. So thanks very much, everyone. Okay, so let's move on. Let's go through the details. As I said in the chat, if you feel comfortable posting your reasoning, then please go ahead and we'll discuss it. If we were in person, this would be a bit more of a discussion, but because this is being recorded, then I don't want to ask you to turn on your microphones and speak. But as I say, feel free to put your thoughts in the chat. Okay, so the solutions. The first puzzle, and this is a little tricky, isn't it? When I've only just introduced this piece of equipment to you, a half-wave plate, to ask you to design a strategy to tell the difference between this and a piece of glass. So we got a range of results in the responses. You'll see, actually, I think all of them were chosen by someone. So quite a lot of you suggested 4 photons, some of you a bit less, some more. So there's actually a way to do this using just 1 photon. And hopefully this is more impressive to you now that you've had a chance to think about it and think about how you would do it. So this is one way in which you can do this, by just using 1 single photon. Excuse me. So you would do this by putting the 2 unknown slides or half-wave plates, the 2 unknown pieces of equipment, next to each other in series, and let the photon go through both of them. And you would prepare the photon in a horizontally polarized state. So you send in a horizontal polarization. Okay, so why does this work? Here are the 2 possibilities where both are the same. Okay, so either both are just glass slides, just a piece of glass, which doesn't do anything to polarization, or both are half-wave plates. So what happens? Well, when horizontally, so this is my attempt at showing a horizontally polarized pulse, by the way, it's just rotated about the axis there. When the horizontally polarized pulse goes through the slide, nothing happens because this is just a piece of glass. When it goes through the half-wave plate, it gets flipped to vertical, okay? Now it goes through the next one. Again, nothing happens if it's just glass. Again, if it's a half-wave plate, it gets rotated again back to horizontal. So if the two pieces of equipment were the same, then you put in horizontal, you get out horizontal, okay? So now if I just stick a polarizing filter at the end, which filters for horizontal, then it will pass through and I'll get a click at the detector. What would happen if they were different? If one was just a glass slide and the other was a half-wave plate, you can probably imagine now it just gets flipped once. And so it goes from horizontal to vertical and doesn't pass through the polarizing filter. So for example, if the first one is a slide, nothing happens here. If the first one is a half-wave plate, then the horizontal becomes vertical. The second one is a half-wave plate, the horizontal becomes vertical, or in this combination, it just goes right through. And so either combination where you've got one of each, the horizontal gets flipped to vertical. Now, this has to be the same setup as what we were talking about for when they're the same. So if this polarizing filter filters for horizontal, this is vertical, it won't pass, and you see nothing in the detectors. So with this setup, with just one single photon, we can determine whether these two are the same or are different, just by seeing whether you get a click in this detector at the end or not. So this is not the solution I was looking for you to come up with, but this is another way of doing it, which ties in a bit more closely to quantum computing. I should say we're at 10 to 8 now, so we might run over a little bit, probably another 5 or 10 minutes. So here's another way of doing this, where this is quite interesting, because even if you can't bring the slides together in the way I showed previously, we can still actually do this using just one photon, using an interferometer. And this is a sort of setup which is used quite a lot, actually, just to learn something about samples. So you can put a sample in here in an interferometer and learn something about it. So how would this work? This time, I'm suggesting that we prepare a pulse which is polarized in the anti-diagonal. So that, and remember, this is the one that when it gets to the half-wave plate, it gets slowed down by half a wave, okay? So imagine that, and this is my attempt at showing the pulse rotated slightly to the, back to the anti-diagonal. Okay, so what happens now? Here's our pulse made up of one photon coming into the apparatus. It hits this beam splitter here, and it splits and goes down in a superposition of both paths. Okay, so just like we've seen previously when we talked about interference. Now, that part of it that's in this path, when it hits the half-wave plate, nothing happens to the polarization, but it gets shifted back. It gets slowed down by half a wave. So it's a bit like having a minus sign, like I said previously. But really, it's just that we're shifted back a little bit. So where we would have expected a peak of the wave, now we've got a trough. Okay. In the other arm, we just have a slide which doesn't do anything to the polarization, and so it just passes through unchanged. So now what happens when these recombine at the second beam splitter here? Well, this has been shifted back by half a wave, so we get destructive interference here and constructive interference here, and everything comes out in this arm here, and we get a click there. Now, you can hopefully convince yourself that if these were the other way around, if the half-wave plate was up here and the slide here, it doesn't matter which is in which arm. We would still get the destructive interference up here and constructive here. So anytime the two are different, it always comes out in this port. If they're both the same, then either both waves get shifted back by a half wavelength or nothing happens. And this gives us our other case of interference, and everything would come out here. Okay. So just another way of doing this. Now, what's different about this case compared to the previous one is we're applying these two operations, these two possibilities, kind of in parallel. So we're doing them at the same time. And I'll come shortly to what this has got to do with computing, just to sort of outline what this has got to do with computing. But in computing, it's of course often very useful to be able to apply operations at the same time in parallel, because you can save yourself time in a computation and make things quicker. Okay, so what has this got to do with computing? This really doesn't look like a computation, does it? And unless you spend far too much of your time thinking about function evaluations, you probably wouldn't think of this like this, but you can think of this whole apparatus as evaluating a function. And so here, the two paths will be the two possible inputs. So input 0 corresponds to one path, and input 1 corresponds to the other. The slide or half-wave plate, whatever is inserted here in the apparatus, corresponds to evaluating the function. So the slide does nothing to polarization, and we would call this a 0. The half-wave plate flips the polarization, and we could call this a 1. And if all you want to know is whether f of 0 is equal to f of 1, whether the two function evaluations are the same, then you can do it with exactly this same apparatus, and you can do it in just one shot. Why is this interesting or important? In any classical implementation, so if you did this classically on a normal computer, you would have to evaluate separately both the function at 0 and the function at 1, and then compare them. So you have to do two function evaluations. So using the interference here in this kind of setup, you can actually do it with just one function evaluation. And as I say, this doesn't look like a computation unless you spend far too much of your time thinking about computations and algorithms. But this was the reason I bring it up this evening, is this was one of the earliest suggested quantum computations. And this is known as the Deutsch-Jose algorithm. Okay, so as for the others, the next one I asked you was, if the two photons enter the beam splitter at the same time, one in each input port, with what probability do they exit in different ports? This was sort of a trick question, because you get interference. So just as we have been talking about interference for single photons or for waves, we also get interference in the two photon case. So intuitively, if you think each photon has a probability a half of coming out one arm and a half of coming out the other arm, then the probability they both come out the same arm should be a half. And in fact, many of you said that in the form, and that really makes sense. What actually happens is you get destructive interference between the two different ways in which the photons can come out at different ports. And so it turns out that for photons of light, when you put them both on a beam splitter like this, they always come out in the same port. So the possibilities in which they can come out different ports is either they both get reflected or they both get transmitted. And it turns out, for reasons that I won't go into in this talk, you get a minus sign between those and you get complete destructive interference. So they always come out in the same port. Why is this interesting or relevant? So this is different behavior to what you would expect classically. And what happens to one photon depends very much on where the other photons are. And so somehow all the possible paths that each photon can take through an apparatus, you have to be also keeping track of all the other photons which are in that apparatus. And so it was pointed out, first of all, theoretically, that if we put together a network of these things, so put all these different beam splitters together in a network and send in single photons at one side, the output of this, so predicting where those photons will come out, or the probabilities of seeing photons in different output ports, because of this slightly different interference behavior, turns out to be hard to compute classically, very hard to compute classically. And so this is the sort of circuit that was done in that photonic quantum computer that I showed you at the start. So it's really just a quantum version of sort of pinball. So you've got these beam splitters where when the photon hits it, it can go one of two ways. But when you put lots of photons in there at the same time, because you get all these interference between all the different possible paths, it turns out to be very difficult to compute classically. Easy to do quantum mechanically because you just set up the apparatus and send through your photons. I say easy, there's some difficult engineering challenges, but you can do it much quicker. And that's what this demonstration of quantum advantage showed. So when I said it didn't do something useful, what this did show was this ability to compute where these photons would come out of a photonic network, which is very difficult to compute classically. And that's kind of the state of the art of quantum computation. Okay, so briefly, let me talk about the very last one. In this sort of prisoner's dilemma, a little bit of a contrived kind of game. The capture comes in, asks each prisoner one of two possible questions. They have to give a yes/no answer, and they have to agree or disagree as by this pattern. Can they win? So again, we got a range of answers for this. It turns out that for this first pattern, there is a strategy which can always win. And all you have to do is when the prisoners are together at the start, they agree how to answer each question. So for example, prisoner A starts by saying, well, if I'm asked question 1, I'm going to answer yes. And then they know that if prisoner B is also asked question 1, they must give the opposite answer. So prisoner B agrees, okay, if you're going to say yes for question 1, then if I get asked question 1, I have to say no because I have to disagree. Okay, and so on. You can just follow through. So now if prisoner B says no here, and these two have to agree, then A must also say no if A is asked question 2. And similarly, the last one, this must disagree with this, but agree with this. So if B is asked question 2, they must say yes. Okay. So this is an example that they can win all the time. And some of you got that. This one, they cannot win all the time. And quite a few of you got the right answer for this, which is that they can only win 3/4 of the time. So just to briefly demonstrate how that works, if they try to do the same thing, so they try to pre-agree a strategy, let's start in the same way. Prisoner A says, if I'm asked question 1, I'll say yes. Prisoner B says, okay, if I'm asked question 1, then I have to say yes as well, because these have to agree. So far, so good. If when the capture comes in, he asks them both question 1, then they both answer the same way and they win and they get freed. Let's continue. So what if prisoner A gets asked question 2? Well, that has to agree with this. So prisoner A has to answer yes there as well. And finally, what if prisoner B is asked question 2? Well, it has to agree with this answer. So it must be a yes. But it's also supposed to disagree with this one. So this doesn't work. They would lose in that case. And so, so it's not possible to satisfy all of those constraints. And you can convince yourself by starting with some other possibility and going through in a different path that there's just no way of satisfying all of these constraints. They can satisfy 3 of them, but not all 4. So what does that tell us? It tells us that for 3 out of the 4 combinations of questions that the capture could ask, the prisoners can win the game and leave. But for the 4th one, they would lose and they don't win. So they win with 75% probability. And you can sort of imagine that if they won, if you then went ahead and played this game and they won more often than that, then you'd start to get a bit suspicious that they were maybe able to communicate somehow, even though you put them in separate cells. Okay, so we're almost done. What has all this got to do with, what has this part got to do with quantum computation? Amazingly, if the prisoners share entanglement, so if when they get to talk to one another, they also manage to set up maybe 2 atoms which are entangled, they both go off to their cells with their little atom, which is entangled with the one in the other cell. Yes, very high-tech prison here, but bear with me. It turns out they can win the game more often. And they do this without communicating. So they just need to share the entanglement at the start. And then they go off into their cells. They take their atom or whatever it is. And when they're asked a question, they go away and they do a little measurement on their atom. And depending on what they see, what outcome of measurement they get, they come up with their response based on that. And they do not need to communicate, but nevertheless, they can win with a higher probability than would be possible classically. Unfortunately, it's beyond the scope of this talk for me to explain why that's 82.5%. If you want to find that out, you'll have to do a physics degree, but it is fascinating. What this game does show is that quantum correlations can be stronger than classical ones. So if they can establish these correlations between their quantum objects, then they can win this game more often. So that tells us that these correlations are different. So what has this got to do with computing? If you imagine you have an array of qubits, an array of quantum bits, then what one qubit is doing can sort of depend on what all the other ones are doing. And that's true classically as well. You can have correlations within a classical computer. But what this game tells us is that the correlations we can have in this quantum computer cannot be directly mimicked by a classical system. So by a normal computer. And it turns out that these sorts of correlations in general are hard to simulate classically. And so the existence of these things tells us that if we can set up a quantum computer, they can do things, they can calculate things that are hard for classical computers to do, just because it's hard for classical computers to simulate these correlations. And I've already taken up way too much of your time, so let's finish with that. So just to summarize, what I've tried to show you through these different puzzles is that due to interference, quantum systems really act differently to classical systems. And they act differently in a way that makes them hard to mimic classically, that makes them hard to simulate. So what this tells us is that a computer which just runs according to quantum mechanics can be hard to simulate classically, and therefore can do things that we can't do on a classical computer. So far, the demonstrations of quantum advantage that we have relied on this. But as I've said from the start of this talk, this field is really moving so quickly. We don't have useful demonstrations yet, but I think they're coming. I think they're coming soon. And I will leave it at that. Thank you very much for your attention. We're a little bit over, but I'm happy to wait if there are any questions. Thank you.